In this video of section 13.5, we'll be doing some examples using the chain rule with partial derivatives. For this question, we're given w equals cosine of the quantity x minus y, x equals t squared, and y equals 1. Find dw dt. You can go ahead and try this one on your own, pause the video, and then come back and check your results. Now, whenever I do these, I like to do the drawing where we have w is a function of x and y, and we have x is a function of t, and y is a function of t. So by finding the derivative of this top variable w with respect to this bottom variable t, you're going to go along the branches, multiply the branches going down, and then add the results. So the derivative of w with respect to t is equal to the partial derivative of w with respect to x times the derivative of x with respect to t plus the partial derivative going this way of w with respect to y times the derivative of y with respect to t. Now notice we have the partial derivative symbols when you are taking the derivative of w, but you have the straight derivative d when you're taking the derivative of x and y. Alright, so let's go ahead and find the derivative of w with respect to t. We're going to take the partial derivative of w with respect to x. You're going to treat x as a variable, treat y as a constant. So the derivative of cosine is your negative sine of that quantity x minus y times the derivative of what's inside, treating x as a variable and y as a constant. And that derivative is 1. Times the derivative of x with respect to t. Now we're looking at the x equation. The derivative of x with respect to t is 2t. Plus, now we're going to take the derivative of w with respect to y. The derivative of cosine x minus y is negative sine of the quantity x minus y times the derivative of what's inside, and the derivative of x minus y when you treat x like a constant and y is the variable, that derivative is negative 1. Oh, running out of space here. But we also want to multiply by the derivative of y with respect to t. Since y equals 1, the derivative of y equals 1 is going to be 0. Now we can simplify this to get our answer in terms of x, y, and t. When you simplify this, you can write it as negative 2t sine of x minus y. And then when you multiply these, that whole thing is equal to 0. Now what we're going to do is replace the x in this equation with what it equals, and replace the y in the equation with what it equals. So we get this all in terms of that single variable t. So it's going to be negative 2t times the sine of x, which is t squared, make that substitution, minus y is your minus 1. So that is our derivative of w with respect to t using the chain rule for partial derivatives. Now, this is not the only way to solve this problem. I am offering this one approach to solving this because you get to practice those partial derivatives. An alternate way would be to go ahead before taking the derivative, make those substitutions, and then take the derivative of w with respect to t. But when you're doing it that way, you're not using the chain rule with partial derivatives. Okay, for this example, we are given w equals xyz, x equals t squared, y equals 2t, and z equals e to the negative t. We want to find dw dt. And if we use that diagram method, we have w, which is a function of x, y, and z. So we've got 3 branches coming out of w, and x is a function of t, y is a function of t, and z is a function of t. So to find the derivative of this top variable w with respect to that bottom variable t, you're going to go along the branches and multiply those derivatives. So our derivative of w with respect to t is equal to the partial derivative of w with respect to x. Now you can use the partial derivative symbols here. However, I like to use this notation w with a subscript x. That means the partial derivative of w with respect to x times the derivative of x with respect to t. That's our dx dt. Plus, moving down this way, the derivative of w with respect to y. It's a partial derivative, so we can use this notation w with a subscript y times the derivative of y with respect to t, dy over dt. Plus, now it's going on this last branch down, the partial derivative of w with respect to z. We can use this notation times the derivative of z with respect to t, so dz over dt. Okay, so let's go ahead and find those partial derivatives. Our derivative of w with respect to t is equal to the partial derivative of w with respect to x. You're treating x as a variable and yz as a constant. So that derivative is yz times the derivative of x with respect to t. That's our 2t plus the partial derivative of w with respect to y. Treat y as a variable, and then x and z are constants. xz times the derivative of y with respect to t. That's going to be our 2 plus the partial derivative of w with respect to z. Treat z as the variable, x and y are constants, times the derivative of z with respect to t, and that's going to be our negative e to the negative t power. One last thing we're going to do is make the substitutions. We're going to replace x with t squared, y with 2t, and z with e to the negative t. So we get dw dt is equal to 2t times e to the negative t times 2t, that's the substitutions here, plus t squared e to the negative t times 2 plus, again, we're going to be replacing the x and y with what it equals. That's our t squared, 2t, and a negative e to the negative t. We can simplify this. This will give us 4t squared e to the negative t plus 2t squared e to the negative t plus 2, let's make it a negative, plus a negative 2t to the third e to the negative t. Okay, now we can say this is our answer. However, we can use algebra a little bit to simplify this. In fact, 4t squared and 2t squared, I would go ahead and write that as a 6t squared e to the negative t minus 2t to the third e to the negative t. You can even further simplify this by factoring out a common factor and writing it that way. Okay, in this one we want to find, we're given w equals y cubed minus 3x squared y, x equals e to the s plus t, and y equals e to the t. Find the partial of w with respect to s and the partial of w with respect to t. Again, I like using that diagram. W is a function of x and y, and x is a function of s and t, y is a function of s and t. So our partial derivative of w with respect to s is equal to, going along the branches starting at the w and ending at the s, moving this way on the branches, multiplying those partial derivatives, we can say the formula is the partial of w with respect to x times the partial of x with respect to s. You can also use those partial derivative symbols, plus the partial of w with respect to y times the partial of y with respect to s. This is going to be our partial of w with respect to s. The derivative of w with respect to x is where you treat x as a variable and y as a constant, and that derivative is negative 6xy. The derivative of x with respect to s, you treat s as a variable, t as a constant, so that's going to be times e to the s, plus the partial of w with respect to y, treat y as a variable and x as a constant. That derivative is 3y squared minus 3x squared times the derivative of y with respect to s. Now here we have y equals e to the t, so we're going to treat t as a constant. That derivative is going to be 0. We can simplify and make the substitutions here to get the partial of w with respect to s is equal to negative 6, making the substitutions for x and y times e to the s, and then all of this is going to be multiplied by 0. So this is one way that we can write our answer for the partial derivative of w with respect to s. Let's go ahead and find the partial derivative of w with respect to t. In this case, we're going to be starting off with w and ending at t. So you're going to follow the branches doing those partial derivatives, multiplying, going down, and adding together so that we get the partial derivative of w with respect to t is equal to the partial derivative of w with respect to x times the derivative of x with respect to t plus the partial derivative of y of w with respect to y times the partial derivative of y with respect to t. Okay, notice in both of these we have the partials with respect to x and y, and then what we're multiplying by is what is changing here. So let's go ahead and find the partial of w with respect to x. That is our negative 6xy times the derivative of x with respect to t. That's going to be times 1 plus the partial derivative of w with respect to y, our 3y squared minus 3x squared, times the derivative of y with respect to t, which is e to the t. Now what we need to do is make those substitutions for x and y in this equation so that we can get this all in terms of s and t. So the partial of w with respect to t is equal to making the substitutions for x, which is e to the s plus, excuse me, sorry about that, e to the s plus t times y, which is e to the t times 1 plus 3 y squared, e to the t squared is the same thing as e to the 2t minus 3x squared, e to the s plus t, all of that squared, that should be a minus, times your e to the t. Now we can go through and simplify this, distribute, combine like terms. That part there is algebra, so I'll leave the answer like this for now, knowing that your answer can be equivalent, algebraically equivalent.